All right, good evening. Welcome back to Statistics. So today we are going to talk about test of hypothesis when sigma is unknown. Okay, so let me go ahead and share my screen and we can get started. Okay. All right. So I'm going to talk a little bit before we jump into your homework so we can do some stuff here. This is very similar to the confidence intervals with sigma unknown, where we have to use something called the t-distribution. Okay, and that's a t-distribution. It's symmetric like the normal distribution, but whereas the normal distribution has very small tails, right? Like that. The t-distribution doesn't have quite as small of a tail. Okay, and the more information you know, the larger the n, okay, we're going to get, if we move up a little bit, okay, the tails are going to be a little bit smaller, okay, something like that, okay. So this would be a low, the blue one would be a low, and will be a low degrees of freedom. Degrees of freedom, I think for maybe when we get to chapter 11, we will not have degrees of freedom this way, but degrees of freedom is going to be n minus 1 is equal to our d of f, okay, d of f. So the blue one would be a low degrees of freedom, whereas the pink one would be a little bit higher as far as the degrees of freedom, okay. So the blue one might be like 5 degrees of freedom, so n would be 6, and by higher df, I would mean like maybe it's 20. So n, sample size would be 21 kind of thing. Okay. So it's mostly like a normal distribution, but it allows for a little bit more error in the tails here. Okay. This was made by a man named William Gossett, and he was doing quality control for Guinness when he kind of came, well, he didn't come up with them, but I mean, he published them. He published them under the name Student, because his employer did not want this to be traced back to them specifically. They didn't want other people to know like how they were quality controlling for their beer. Okay. So if they made him publish under a pseudonym, this is the pseudonym he chose. He was a very humble guy. Okay. Unlike if you ever get a chance to read about 19th century statisticians, they were not, most of them were not very humble. Okay, there's a lot of stories with there's a lot of drama. All right, but this is the distribution that we have, and we need two numbers. We need a confidence. We need an alpha, right? Just like in the other one, right? We said alpha is equal to 0.05 or 0.01. Okay, so we need that. And we also need our degrees of freedom. Okay, because that's going to tell us what kind of curve we have. And we're just going to look these up on our table. Okay, well, we're going to do it for the first problem. We're not going to do it for the rest of them. The calculator knows this stuff. It's going to take a little while to calculate it because the formula is a little bit more involved. But for the most part, it's a very similar technique that we use for the normal distribution. The same 5 steps for test of hypothesis are going to be exactly the same. Actually, the same steps for test of hypothesis are the same regardless of what happens. The calculated test statistic is going to be maybe wildly different, but the same 5 steps are going to be there. Okay, like I said, calculate the test statistic might be easier said than done, but everything else is going to be the same kind of steps. Okay, so the first little part of this deals with like some interpretation of a table. So I'll kind of show you that now, but yeah, we're dealing with sigma is unknown, and quite frankly, when I learned about excessive hypothesis or confidence interval, and they said, here's sigma, like, that seems a little contrived, just a little. I mean, when do you not know this? You don't know the mean, but you do know the standard deviation? Like, that doesn't make any sense. Standard deviation seems so much harder to figure out. Like, why would I know the standard deviation? It's because they have to teach this thing to you one at a time. And even though there are situations where you might have a population standard deviation, for the most part, you won't. So it's a lot of 9.2 and 8.1. It's entirely contrived. Okay, we lied to you. Let's just be able to do this under two parts rather than just doing under one. Can we do that? No. How about this? Kind of. All right. So here's what we have. So let me look at the problem. All right, we have a scenario here. We have a t value. Okay, and this is, again, this is to kind of give an appreciation of what we did before calculators. This is not a something that you're necessarily going to be doing. So I'm a little confused as to why this is part of your homework, but okay, so be it. I would not quiz you on a question like this, by the way. So if you're like, I was a little confused, I'm like, that's okay. I will never make you face it alone. So we have t is equal to negative 2.588. My n is 22. What does that mean about my degrees of freedom? It's 22 minus 1 is 21 degrees of freedom. And we want, right, a mu is not equal to mu naught. That means we have a two-sided test. I really wish they would have started with a one-sided test, but here we are. They give us the hardest one first. So what we're going to do is we're going to look on our table, right? We have, oh, what's our alpha? Oh, we have to find the alpha. So we're given a t, and they don't publish like the other side of it. They just publish this. So if you want the negative, you put the negative in, and otherwise you leave it as positive. Okay. So the negative, that just drops off for what we're doing with this table. We'll get back to what we need for that a little bit later. So what are we going to do? We are going to go to our values here. And we have, so the first thing you know is that we have degrees of freedom of 21. You are now locked into this row. Okay, you must use the row 21 here because that's how many degrees of freedom we have. That's what the curve says. Okay, and what we're going to do is we're going to find two numbers that are around 2.588. Okay, so it looks like 2.588 is between $2.52 and $2.83. It's somewhere between these two values here. Do you see that? It would be way bigger than this one, but they are between these two values. Okay, so I'm going to go ahead and go up because the area in the right tail here, okay, is 0.01 to 0.005. Okay, so 0.01, 0.005, and my p-value is somewhere between these things. Okay, my critical value is my critical value what is that, 2.588, back down here to 21. 2.588, it's between 2.581, 2.581 and 2.831. 2.831. All right. So, but we're running a two-sided test. So we actually don't use these values. We have to multiply by the number of tails. Okay. We have two tails. It's a two-sided test. So my p-value is actually somewhere between 2 cents and twice half a penny, right, is 1 cent. So my p-value is somewhere between 0.01 and 0.02. And without a calculator, that's as close as you could get. Okay. Now, if my p-value was 0.0, if my alpha, right, was 0.01, well, I know that this is strictly bigger than 0.01. Okay, whatever my p-value is bigger than 0.01. So I say my p-value is larger than alpha, which means do not reject the null hypothesis. Okay, so, but that's the best that we had. If you had a 0.05 to a 0.02 p-value, and you decided for some bizarre reason that your alpha is 0.03, I couldn't say anything about it. I have to say, well, it might be, but it might not be. So we always give the benefit of the doubt to the null hypothesis. So we would say, do not reject the null hypothesis. I don't have enough evidence to say one thing or the other. Okay. So back in the day, we'd have to carefully select our problems for textbooks to be able to tell people like you're going to be able to get an answer, as opposed to, oh, okay, if it's an ambiguous case, you got to give it to the null hypothesis. Okay. So computers are going to do this for us now, but we still need to know. Okay. So this, by the way, I'm never going to quiz you on this. Okay. So I know here, multiply by 2 to get the tails, so 0.02, half a penny times 2, 0.01. So my p-value is somewhere between 0.01 and 0.02. Okay, so let's go back to our homework here. Okay, this is 0.01 and 0.02. Now, next one, it's a one-sided test. Excuse me. Okay, we're only going to do one more. Well, we're going to do this one and we're going to move on. But it's a one-sided test. Okay, so our test is going to be H1 less than, oh no, H1 is, sorry, mu is less than mu1. Okay, our alternative, some value, 0. T was negative 1.745. My N was 18. 18 minus 1 is equal to 17. By the way, the calculator does this for you. Okay, so you don't have to worry about, did I subtract 1 for the standard, for the degrees of freedom or not? The calculator is already taking that into consideration. All right. So again, we have to look this thing up on a table. Okay. So we have our degrees of freedom of being 17. So we are locked into this row. Okay. And I need to find values that are in and around 1.745. Okay, so we are here, we're at 17. 1.745 looks like it is between 1.34 and 2.101. Okay, so here we go with 17, 1.740 and 2.11L. Okay. So that's my p-value, that's my critical value. Okay, let me go ahead and take a look at what's going on here. 1.745. And again, we do drop the negative sign. Okay, because they only publish half of the table. That was just fine because it's symmetric, so you can just fold it over and get the other half. All right. So here we were with this guy. Where was we? Points this one right here, these two. Okay. So if I scroll all the way up, we have 0.05 and 0.025. Okay, this is 0.05, 0.025. My p-value is here, but what do we have to do here? Okay, you have to multiply by 2. Okay, so even though, okay, they're going to swap because we're talking about the area for a triangle versus the value that we're going to use here. It used to drive me, it still drives me nuts when students would write these things backwards. Like they would write No, that's the correct way. They would just leave the values like this. So they would write 0.05. I don't really take off for it. I just mark it like, hey, pay attention to what you're doing. Because what you're telling me here is somehow a nickel is worth more than a dime. And I could trade you that. That would be fine. I would love to make that trade with you. If you think a nickel is more than a dime because it's bigger, I guess, I don't know. But I would usually mark this wrong, not mark it. I wouldn't take points off, but I circle it and like, look, I know that you know that a dime is more money than a nickel. Okay, so please show me that. Okay, show me that you know too. Okay, so that's what would happen with that. But here my p-value is somewhere between a nickel and a dime. So there we go, and we'll go back to our problem here. Okay, p-value 0.05 and 0.10. Okay, and that's how we would make our decision. So if we had some kind of weird alpha where it's like 0.66 or 0.66, 0.066, right, I wouldn't be able to tell you. Okay, now, oh, what did I do wrong? N is equal to 17, right? Or N is equal to 18. 18 minus 1 is 17. 0.01. Oh, it's one-tailed. This isn't a two-tailed test. Okay, so we're just going to go with this guy right here. Okay, we're just gonna stick with it. So this is going to be a nickel and 2.5 cents. Okay, so I was making it harder than it was. It wasn't that hard. We don't multiply. It's one-tailed test, right? One-tailed test. We don't have to multiply by 2. So we do get to say 0.05 is a bigger number than our p-value, which is a bigger number than our 2.5 cents. Okay. Again, I don't know what p-value is, but I just realistically, this is harder to do in math than it is in real life. Okay, like I know my water bill is going to be between certain values. If all of a sudden it's $10 more, I've got some questions. If it's double, I've got a lot of questions. Okay, so generally people use the same amount of gas. Well, not exactly, but close. Okay, but you know what your December gas bill looks like generally. Okay, and if all of a sudden it changes, you're gonna say, wait a minute, what happened? Okay, I need to know what's going on. Do I have a leak somewhere? What's happening? 0.025. So we do this automatically. If I asked you like how much is your water bill, and you're the one who actually pays it, you're going to be able to say, oh, it's between $50 and $60, or oh, it's between $60 to $70, whatever it happens to be for you. Okay, but you're going to know. So that's what you're doing here. So I don't know what it's going to be, but I do know that I can expect to pay at least $60. But if it's $70, I'm going to have a question. All right, and that's a little bit better for them. Okay, again, going back to this, we would have to multiply by 2 because it's a two-sided test. All right, and then so on. But we don't really do that anymore, so we're pretty good. Okay, so moving on to something that you might. Okay, so a new weight loss pill is given to 12 overweight adults. Each adult is weighed 2 weeks later, and weight loss is recorded. Okay. Following is a box plot for a random sample. Is it reasonable to assume the conditions for forming a hypothesis test are satisfied? You need 2. Count them. 1, 2 conditions. 1, the underlying distribution, right? The distribution is approximately normal. Okay, so that's one thing we need to know. Again, n greater than or equal to 30 in order for us to have normality. But historically, t-values generally used for small sample sizes. So we should do a test to see whether or not that's true. And the second one, and this is a little bit more important, no outliers. Okay, if you ever take like a more advanced stats class, they say, well, why don't you kick the tires and make sure that, see what happens. This was a pretty light assumption to make. So if it was kind of normal, it's good enough. If you have like one outlier, no, your results are going to be completely off. So this was a really, really important condition. Okay, but your book doesn't tell you that because you're not at that level, so that's fair. But both of these things have to be satisfied, that we need approximately normal and we cannot have any outliers. Okay, and again, I'm not going to put a whole dressing on a sample and say, go ahead and figure that out. Okay, if I'm going to ask you something like that, there's going to be like an A, B, C, D, and you're going to tell me whether or not it's appropriate or not for that value. But there are no outliers because there's no little dots at the ends here. I wish they would have given me some kind of a title. And this is more or less in the middle. I mean, it's a little skewed, but I wouldn't say it's like really far over to one side or the other. So we would say there is no evidence of a strong skewness. A little bit, sure, but not a lot. So we should, say that the population is normal and it is reasonable to assume that the conditions are satisfied. We can proceed with the problem. Okay, so we have that. All right. Oh, they give us a whole, do we have to do a whole problem? We do, maybe, yeah. Cool. Okay. So let's read it here. It says the mean annual tuition and fees in the 2013 to 2014 academic year for 13 private colleges was $38,500. It's a lot of money. With a standard deviation of 7,000. The dot plot shows it is reasonable to assume. Thank you for listening to that. Okay. And this is generally the way that my problems are going to be structured as well. Like it is reasonable to assume that the population is approximately normal. I'm not leaving that up to you. Okay. Can you conclude that the mean tuition and fees paid for a private institution in California differs from $35,000? Use alpha equals 0.01, I'm sorry, 0.10, and calculate this with a calculator. Okay, so 1. Set up or test of hypothesis. HO, H1. Okay, let's have a look at what's going on here. So it differs from $35,000. Okay, does differs mean more than or less than? Or does it mean not the same as? It means not the same as. They just wanted it differs than. They're not saying it's better or it's higher or lower. We don't care. We're just saying is it different from. So we're doing a two-sided test here. We came in with alpha equals 0.01 or 0.1 rather. So here's our first step. Here's our second step. Third step is we're going to calculate a test statistic. So if you want to write this down because like you're used to practicing the steps that way, that's fine too. Just telling you don't have to write it down. So if you didn't memorize it this way or didn't practice it this way, that's okay. We're going to go to statistics. We're going to go to tests. Okay. Hey, look at that. Number 2 is a t-test. That's what this is. Okay. So this is a t-test. All right. Let's write down the pertinent information we have for that. I wanted to put you away. Okay. We have a sample mean, right? With me. Sample of 13 private colleges is 38,500. So our sample mean is 38,500. Our N, they asked us to do 13. And we have a sample standard deviation, right? Not a population standard deviation, a sample standard deviation of 7,000. By the way, if you're struggling a little bit with the grammar and how this is put together and how you're supposed to pull these things out, you're not alone. Okay, so we try to be really careful when we write these things down. But look, tuition and fees for the academic year for a sample of 13 private colleges in California was $38,000. The $38,500 is referencing the sample. Okay. If the standard deviation is 7,000, the 7,000 is referencing the sample. Okay. So it's really, there's a lot of reading comprehension in this section. Okay. So we have that. Let's go back to our calculator here. We have a t-test. Okay. We're not going to give it data. We're just going to do stats. Okay, because we only have some really surface level sort of statistics on it. They didn't give you 13 numbers. Okay, so we're going to say mu is equal to 38,500. Okay. No, 35,000. That was the thing we're trying to compare it to, is 35,000, because it's down here. Okay, 35,000. Do not decide that since it's the second number listed, it's going to be that. You actually have to read this thing to figure that out. Okay. Sample standard deviation, 7,000. Okay. And 13, right? We looked at 13 colleges. Okay. And in this case, we want, right? We want two-sided. Okay. And there we go. Right. So here we are with what's going on here. Okay, our test statistic is 1.802. Okay, just imagine how much fun it would always be to look these things up on the table. Okay, trust me, it was a lot of fun. Okay, our p-value is 0.0965, 0.09. I'm going to go 66. Okay, that's our p-value. Okay. And then everything else we don't really care about. Okay, we're just using this like, okay, everything else, they're just reporting what we typed in so that we know. Okay, so alpha equals 0.10. Okay, alpha equals 0.10. How does 9 cents deal with 10 cents, right? Is our p-value bigger or smaller than alpha, or is it too hard to tell? Right? That's a little smaller, isn't it? Okay, so this was our standard. If we fall below the standard, we're going to have to seek some sort of alternative explanation for what's going on. Okay, so we're going to say reject the null hypothesis. Okay, there is evidence to say that these are not the same. Okay, we conclude the tuition for private colleges is different than, because that's what we tested for, the $35,000. Okay, I mean, clearly it's a little bit higher, but we can't say that. All we can say is it's different than, it's not the same as. Okay, so what is our, okay, so let's go back and look at all of this. Okay, this is mu is equal to 35,000. Okay, this one is mu is not equal to 35,000. And notice we didn't do anything. We didn't change what the p-value was. We didn't multiply by 2. We didn't do any of that. Calculator takes care of it. Oops. Can I do this? Control Z. Control Z. No. Almost. Mu equals 35. Oh. Okay. Hypothesis is a two-tailed test. All right, we'll check. Right. Oh, they like the commas. Compute the p-value. We did that. Okay, so we'll go back to our thing. We said the p-value is 0.0966. 0.0966. I believe I did round to 4 decimal places. Okay, all right. So we're going to say reject the null hypothesis because our p-value is smaller than our alpha. Okay. And then we have to say, what the heck does this mean? Because you can't just say reject HO. I'm not going to know what that is. Okay, I'm going to feign not knowing what that is. You got to tell me. There is enough evidence to conclude that the mean tuition and fees differs $35,000. Right? There's your blueprint of how to do this. And they all work this way, okay? They all do. All right. Let's do this one, and then we will break and do the rest of them in the next one. So we have National Health Statistics Report described a study in which 315 one-year-old baby boys were weighed. Their mean weight was 25.6, standard deviation 5.3. Pediatrician claims that the weight of one-year-old boys is greater than 25 pounds. Does this data provide convincing evidence? Alpha equals 0.05. Great. Let's write this down. Okay. So we have HO mu is equal to 25 H1 greater than, mu is greater than 25. 1 second here. All right, so here he is making all the noise. He's Gregory. He's a very friendly kitty. He never met anything that he doesn't think he should be best friends with. So, although I think I probably held him up enough that he's going to get a little interested in everything else except for me. But when you hear the noises, that's this guy. All right, you're going. Off you go. Okay. Yeah, I know. I know. All right. So there's my guy there. All right. So, okay. I think he's 25 pounds. It's a big cat. Okay. So let's see here. We're on a one-sided test. We said alpha is equal to, all right, alpha is equal to 0.05. Okay. So that's our step one. That's our step two. Okay, here's step one. It's the whole thing. Okay. Now we're going to calculate our test statistic. All right. So here's our test statistic. It is, so we're going to write some stuff down. Okay, so we found that X bar was equal to 25.6. N and our S. How many babies did we get here? We got 315. Okay, and then S was 5.3. So this was one of the joys that we had to work with with the tables. Okay, so we'd have to look up the degrees of freedom here. There ain't 314, is there? Like, no, we just have to like estimate it and use the highest number we had. So fortunately, that's not something you get to experience, okay, because that was a cause for a lot of confusion. A lot of students had a lot of trouble with that, and I'm actually glad that that part of this is gone. Okay. So our test statistic is TI 84 t-test. Okay, and let's see what's going to make us do. Okay. So we're going to go to stat. We're going to turn it on. We're going to go to stat, test, t-test. Okay, and we are still typing in no, we're typing in stats. Okay, so how much did we say? We said 25 pounds. Okay, X bar was 25.6, 25.6. We had 5.3 as a standard deviation. We had N is 315. Fortunately, they can figure out the standard deviation or the degrees of freedom for 314. We don't have to worry about that. Bigger than, so this is the first time we've seen a right side of the graph. Okay, so we'll go ahead and calculate that. Okay, and here we go. Here's our test statistic is 2.009. Again, before all we could do is tell them, oh, it's between this one and that one. Okay. P-value 0.0226, 0.022, we'll say 7, okay, for the rounding. Okay, and yeah, there we go. We're good to finish the rest of the problem here. Okay, so we oh, let's finish the rest of the problem on our side rather than on theirs. Okay, alpha equals 0.05. Which one's bigger, p-value or alpha? Right, so here's our p-value, 0.0227. Our alpha was 0.05. This one's smaller. Okay, this was our level of significance. We said, well, if it's bigger than this, random chance. What are you going to do? But it's smaller, so we're going to say reject the null hypothesis. Okay, we have to find an alternative. Reject HO if there is enough evidence to show that what level of baby is this? 1-year-old, 12-month boys, to show 1-year-old baby boys are more than 25 pounds. Okay, something like that. All right, so let's go back to our thing. Okay, so we're going to say HO is equals 25. And what were they trying to show? Trying to show that it is greater than. Okay, so we're going to have mu is greater than 25. Okay, this is a right-sided test. All right, repeat the p-value to 4 decimal places. Okay, we did that. That's good. We're going to say 0.0227. Okay, so 2 in there. All right. So we said that we are going to reject the null hypothesis because this fell under our standard. Okay, we made a standard and said we fell under it, so we have to find an alternative hypothesis. Okay, and now we're going to say there is enough evidence to conclude that the mean weight of 1-year-old boys is greater than 25 pounds. Boom, there you go. All right, I'm going to go ahead and stop this, and that way the videos won't be too long, and I will finish this up in part 2. All right, thank you.